Alright, this is chapter 6 homework for Physics 201. It says a pitcher claims he can throw a .145 kilogram baseball with as much momentum as a 3-gram bullet moving with a speed of 1,500 meters per second. What must be the baseball's speed if the pitcher's claim is true? That's saying that the momentum of the baseball is equal to the momentum of the bullet, and so that's the mass of the baseball times the velocity of the baseball is equal to the mass of the bullet times the velocity of the bullet. So the mass of the baseball is 0.145 kilograms. I want to know what the velocity of the baseball is. The mass of the bullet is 0.003 kilograms, and the velocity of the bullet is 1,500 meters per second. And of course, this is significant. 0. And then if I solve this for the velocity of the baseball, I find that the velocity of the baseball is 31 meters per second. All right, that's about 70 miles per hour. So not an insanely fast baseball that has the same momentum as a bullet. However, we know that a bullet is much more deadly, so how do their energies compare? Now, the kinetic energy of the baseball is 1/2 mv squared. With the mass of the baseball and the velocity of the baseball, that's going to be 1/2 of 0.145 kilograms times the velocity of the baseball, which is 31 meters per second, squared, and that's equal to 69.7 or 70 joules. All right, and then the kinetic energy of the bullet, which is 1/2 times the mass of the bullet times the velocity of the bullet squared, 1,500 meters per second squared. I get 3,400 joules. So see, the bullet has a lot more energy than the baseball, even though they both have the same momentum. So that's why it's more deadly. A 1/2 kilogram football is thrown toward the east with a speed of 15 meters per second. Stationary receiver catches the ball and brings it to rest in 0.020 seconds. What is the impulse delivered to the ball as it is caught? All right, well, impulse we call I. This is just the change in momentum. Remember, this is a vector quantity, and that's going to be P final minus P initial. So P final is 0 because that's the momentum of the ball. It comes to rest, minus the mass times the velocity. That's the initial velocity. So it's going to be negative of the mass, which is 0.500 kilograms, times the initial velocity, which is 15 meters per second to the east. So V naught is equal to 15 meters per second. That's going to be positive in the I direction because it's to the east. All right, so times 15I. So my impulse is going to be negative 7.50. That's in kilogram meters per second. And it's in the I direction, or towards the east. Or actually negative I direction, which is going to be towards the west. Now I want to know what is the average force exerted on the receiver. Well, that force is going to be delta P over delta T. Actually, this should say what is the average force exerted on the ball by the receiver? What is the force required to bring this ball to rest? All right, so that force and the momentum are vector quantities. You could also write this as dP dt. I'm going to talk in calculus terms. But I've already found my delta P, and it's negative 7.50 kilogram meters per second in the I direction, divided by my change in time, which is 0.020 seconds. And so my average force is negative 375 newtons, and that's in the I direction, R to the west. That force is exerted to the west. A 730 Newton man stands in the middle of a frozen pond of radius 5 meters. All right, so here's my pond. I have a guy here. This distance is 5 meters. He is unable to get to the other side because of the lack of friction between his shoes and the ice, so 0 friction, we assume. To overcome this difficulty, he throws a 1.2 kilogram physics book horizontally towards the north shore. So he throws a book in that direction. How long does it take him to reach the south shore? So we need to find the velocity of this man. In order to find the velocity, we consider the momentum. And we can say that the initial momentum is equal to the final momentum. Now initially, neither the book nor the man are moving. So the initial momentum is 0. In the final momentum, we have the mass of the book times the velocity of the book plus the mass of the man times the velocity of the man. All right, so I can put in my numbers here. The mass of the book was 1.2 kilograms. The velocity of the book is 5 meters per second. That's in the positive j direction towards the north, plus the mass of the man. It says that his weight is 730 newtons. That's 730 over 9.8. And I get a mass of 74 kilograms. All right, so I got 74 kilograms times the velocity of the man, and that's what we want to solve for. And I find that the velocity of the man, solving this equation and keeping the appropriate vector notation, is minus 0.081 meters per second in the j direction. All right, that means that it's to the south, just as you'd expect. So the man throws the book to the north, he moves to the south in order to maintain that 0 momentum, the conservation of momentum. Now I want to know, how long does it take him? Well, my time is going to be x over v, the distance over the velocity, both vectors. X is negative 5 meters in the j direction. V is negative 0.081 meters, also in the j direction, and I get my time of 62 seconds. Takes them 1 minute. All right, that assumes 0 friction. That's not entirely true, even on an icy surface, but just assuming 0 friction. That is true in other situations, like in space, for example. There's 0 friction. On some apparatus on the Earth, there's 0 friction. All right, a rifle with a weight of 30 newtons fires a 5-gram bullet with a speed of 300 meters per second. Find the recoil speed of the rifle. So what I have here is this rifle. I should go the other way. And then there's a bullet coming out of it. All right. Initially, the momentum is 0 because neither one is moving, but the final momentum is the rifle has a certain amount of momentum and the bullet has a certain amount of momentum. And those are going to add up to equal 0 because the initial momentum is 0. So I can take the conservation momentum, that is at pi equals pf. Excuse me, I think I've been calling this p naught. Doesn't really matter. P naught is equal to pf. So P naught, as we already said, they're both stationary, so it's 0. And PF is going to be the mass of the rifle times the velocity of the rifle plus the mass of the bullet times the velocity of the bullet. All right, I'm looking, let's see, the mass of the rifle. It says it has a weight of 30 newtons. To find that mass is going to be 30 over 9.8, as I did in the previous problem. That gives me a mass of the rifle of 3 kilograms. Just keeping one sig fig. And then the mass of the man is 700 newtons over 9.8. That gives me his mass to be 70 kilograms. All right, so I have the mass of the rifle is 3 kilograms. The velocity of the rifle, which is what I want to know, the recoil speed, plus the mass of the bullet, which is 5 grams, which is 0.005 kilograms. And then the velocity of the bullet is 300 meters per second. That is in the positive I direction. All right, if I solve this for V of the rifle, I find that it is negative 0.5 I meters per second. Negative 0.5 I meters per second. So that's this velocity. It's in the negative I direction at 0.5 meters per second. All right, now consider the rifle being held by a man. And so now our system has changed quite a bit, because now I don't just have the rifle, the mass of the rifle to consider. I have the mass of the man as well. All right. So my initial momentum is still 0, and it's equal to the final momentum. So 0 equals the mass of the rifle plus the mass of the man times the velocity of the recoil velocity, the recoil speed, plus the mass of the bullet times the velocity of the bullet. And here I'm going to be looking for that recoil velocity of the man and the rifle. All right, so I can put in my numbers here. I have 0. The mass of the rifle plus the mass of the man is 73 kilograms times the velocity of the rifle. This is just like we had before, 0.0050 kilograms times 300 meters per second. That's in the I direction, just like before. And then I solve for VR, and VR is going to equal negative 0.02 meters per second in the I direction. In the I direction. So you see, it's quite a bit different than it was for just the rifle alone, which is a half a meter per second. Now we're a full order of magnitude off by having the man hold the rifle, so it increases the mass of the total system. All right, a 950 kilogram compact car is moving with velocity. It's given. It collides with a hay wagon, and they stick together. All right, so my car is moving sort of in this direction. The hay wagon is also sort of moving in that direction. Let's see. The hay wagon sort of moving in that direction. But then they stick together, and they become one body, and we want to know what is the velocity that they're moving at. So this is a simple, although two-dimensional, conservation momentum problem. So I say P initial equals P final, P naught equals PF. All right, and my P initial is going to be the mass of the car times the initial velocity of the car plus the mass of the hay wagon times the initial velocity of the hay wagon. I should have a 0 here for the initial velocity of the car. And then that's going to equal the mass of the car plus the mass of the hay wagon times my V final. These are all vectors. All right, because they stick together in the final scenario, they both have the same velocity. So I can just add up their masses. All right, I'm going to start putting some numbers in here. Mass of the car is 950 kilograms. The initial velocity of the car is 32I plus 17J. That's in meters per second. Plus the mass of the hay wagon is 450. Times the initial velocity of the hay wagon is 12I plus 14J. And that's equal to the mass of the car, 950 plus 450, which is what, 1400? All right, 1400 times the final velocity. And then I solve this for the final velocity. Let's see. This is going to work out. I'm going to multiply this times this number and this times this number and add those two numbers together, and it works out to be 36,000 in the I direction. So I add up my I terms, and then I multiply this number times this number and this number times this number, and I add those together, and that gives me 22,000. That's in the J direction. And then I divide by the 1400, which is the total mass, and that'll give me my final velocity in vector notation, which is 26I plus 16J. And that's my final answer. I think I asked for it in, yeah, I didn't specify, but that's it in vector notation. It's in meters per second. All right, a cart with a mass of 0.34 kilograms moving on a frictionless linear air track at 1.2 meters per second strikes a second cart of unknown mass at rest. The collision between the two carts is elastic. Elastic, that means that energy and momentum are both conserved. So initial is equal to the final momentum, and the initial energy is equal to the final energy. All right, so I have two sets of equations that I can deal with, either from the momentum or the energy. After the collision, the first cart continues in its original direction at 0.66 meters per second. What is the mass of the second cart? And what is the velocity of the second cart after the second cart? The velocity of the second cart after impact. All right, so I have two unknowns here. I don't know the mass of the second cart or the velocity, the final velocity of the second cart. So I'm going to need two sets of equations. And I can create two sets of equations by looking at the momentum. That is P naught equals P final. And then also the energy, E initial equals E final. All right, so equation one, it's going to be my first equation, that P initial is just the first cart. So it's going to be M1 times V naught 1. All right, because it says that the second cart is at rest. So I'm going to leave that out because it has zero velocity, so it doesn't contribute to the momentum. P final is going to be M2 or M1 V final for that first cart plus M2 V final for the second cart. All right, so that's my first equation. My second equation is from the energy. E initial equals E final. All right, there's only kinetic energy involved here. So my first one is going to be 1/2 M1 V naught 1 squared. Remember, the second cart is initially stationary, so it has no energy. The final energy is going to be 1/2 M1 V final 1 squared plus 1/2 M2 V final 2 squared. All right, so there are my two sets of equations. Let's see, my unknowns are M2 and V2F or VF2. So I don't know either one of these unknowns, and I need to find out what both of them are. But you have a system of two equations and two unknowns, so you can solve for both of those. I'm going to solve equation 1 first for M2. So I'm going to solve for M2. Go back to blue if that's okay. M2 is equal to M1 V1 naught minus M1 V1 VF for divided by VF2. All right, I'm going to drop the vector notation here because I'm dealing in one dimension, and so my direction for these is going to be either positive or negative. Positive or negative. So I'm just going to drop it from here on out. It's all in the I direction, and the direction is going to come out as either positive or negative in the end. All right, so that's my equation for M2. Now I'm going to plug this in over here for M2, and then I'll have an equation with only one unknown. All right, so I have, I'm going to have to write a little smaller. Actually, I'm going to give myself a little bit more space here. One half M1 V naught 1 squared equals 1/2 M1 VF1 squared plus 1/2, and now I sub this in for M2, M1 V01 minus M1 VF1 divided by VF2 times VF2 squared. Unfortunately, this cancels, so I get rid of that pesky little square for VF2, which is really what I want to know. I want to know what is VF2. I'm going to go ahead and put in some numbers here. I have 1/2 0.340 times V01 is 1.2 squared. 1/2 of 0.340 is VF1 squared. It's 0.66. Alright, that comes from, says it's moving at 1.2 meters per second, and then the first cart continues in its original direction at 0.66 meters per second. So I'm assuming that this is in the positive direction, and so that's also in the positive direction. Alright, plus 1/2 of 0.340 1.2 minus 0.340 0.66 times V2F. Alright, and then I solve that whole darn thing for V2F. I get just to help you make sure we're tracking along, I get 0.245 equals 0.0741 plus 0.092 times V2F. Now if I do that, I get V2F equals 1.9 meters per second. And it comes out positive, and that's, as we said, it's in the I direction, or in the plus X direction. Now, I can also find M2, and I already have an equation for M2 here. I just plug in the numbers here for M2, because now I know all of these values. I'm just going to give it, I get 0.097 kilograms by plugging the values that I now know for V2F. And that's a lot of algebra, and it's a lot of places to make a mistake. So a good way to check these are to take the numbers and to plug them back into equation 1, and just to make sure that the left-hand side agrees with the right-hand side, that momentum, with those numbers, that momentum is actually conserved. Or you can also do it with this equation too. All right, I recommend that, especially if on a test, if you have extra time, that you just go back and check that, because while, I won't count off all of the problem for just a small mistake, I will count off some. If you have a small calculation error that gives you the wrong answer. All right, number 6, 7, this one's slightly more involved. It's a similar problem. It's an elastic collision, so energy and momentum are conserved. I'm just going to write down what we know up here. I have a bowling ball and a bowling pin. Mass of the ball is 10 kilograms. The initial velocity of the ball is plus 2 meters per second. And again, I'm going to drop the vector notation, the I, because it says that its motion is one-dimensional. So we'll say that it's all in the I direction. And so I don't need to worry about distinguishing between I, J, or K. So I'm just going to drop the vector notation, and the plus minus is going to tell is it in the plus X direction or the negative X direction. All right, VFB, the final velocity of the ball. I don't know what that is. It's not asking that, but I don't know what it is. And then I also know some stuff about the pin. The mass of the pin is 1 kilogram. The velocity, the initial velocity of the pin is 0. It's at rest. And I want to know what is the final velocity of the pin. All right, so I can write two equations. P naught equals PF. These are my knowns, or unknowns as it may be. So I can say P naught equals PF. Again, dropping the vector notation, but keeping in mind that I have to add my plus or minus if it's in the plus or minus direction. So I have MB V naught B equals, I'm leaving off the pen because it's initially at rest, so it has no momentum, MB VFB plus MP VFB. Alright, I don't know VFB or VFP. I don't know either one of those. Now, I can also do my energy. E initial equals E final. That's going to be 1/2. It's only kinetic energy. MB V naught B squared. That's for the bowling ball. Equals 1/2 MB VFB squared plus 1/2 MP VFP squared. And again, I don't know this or this, but in particular, I'm looking for this value. So I need to create an equation through substitution that only has VFP in it. And in order to do that, I'm going to solve this equation for VFB. And then I can take that expression and put it in place there. And it'll give me an equation that only has VFP in. And then I'm practically done. All the rest is just algebra. All right, so I'm going to solve this for VFB, and I get MB V naught B divided by MB. Whew. Okay, so now I'm going to plug that in over here. I'm going to sort of cordon this off. I'm going to plug it in over here. And this is where I put it in. Remembering that this term, this whole term is squared. Just make sure I've got that right. MB minus V naught B. Okay, so far so good. Plus, I have to add this other term. 1/2 MP VFP squared. Alright, so I'm looking for VFP, and in this equation I know everything but VFP. Alright? I'm going to go ahead and put in some numbers, because this is a big old jumble, and I find it easier to put in numbers. Other people don't, but I find it a little easier to put in numbers. 1/2 of the mass of the bowling ball, that's 1/2 times 10 times V naught B squared. That's going to give me 20 over here. That's going to be 20 joules, actually. And this is going to be here. I can get rid of make a substitution or simplify this and get 1/2 MB. Basically, I'm canceling out this MB with one of these MBs, okay? And that gives me an MB in the denominator on that side. Inside the parentheses, I get 10 times 2 minus 1 times VFP. That's all squared plus 1/2 of 1 times VFP squared. All right, now, so I can continue on. I get 20 equals 1/20 times 20 minus VFP squared plus VFP squared over 2. All right, I have nothing but VFP. It's starting to look a little bit better. I can make this 400, multiply both sides by 20. It's 20 minus VFP squared plus 10 VFP squared, because remember I multiplied both sides by 20. Now I want to multiply out this term. using foil. All right, it should look like that. Now let's see, I've actually made a mistake here, I think. Yeah, so this goes away, so I get 0 equals negative 40 VFP. No, I'm sorry, this should be, no, that's right, negative 40 VFP plus 11 VFP squared. All right, now I can solve this. 0 equals VFP times 11 VFP minus 40. All right, I just factor out one of those VFPs, and then this equation has two solutions. That's VFP equals 0, but that doesn't really make any sense in our physical scenario because we know that it moves. And then I also have 11 VFP minus 40 equals 0. And if I solve this for VFP, I get 40 over 11, which is what? 3.6. 3.6 meters per second. All right, now you can check this answer. You can take that VFP now, solve for VFB right here, and then plug both of those back into this equation. I won't do that here because it's fairly intensive. But on the test, if you have something like this, I'm going to mainly count most of your credit sort of up to this point, creating the equations, and then all the algebra that follows, it'll be worth value, but not that much less than the actual meat of the problem. All right, let's move on. Number 8. By the way, this is a real useful calculation actually, and when you're studying ideal gases, the collisions between molecules are elastic, so they conserve both momentum and energy. So you can calculate what are the paths that particular molecules or atoms are going to take in a gas by solving the system of equations that you can derive from their conservation of momentum and their conservation of energy. And that's done sort of in classical thermodynamics. A neutron, mass 1U, strikes a deuteron, mass 2U, and combined to form a tritium nucleus, which has a mass of 3U. If the neutron's initial velocity was that, and the tritium leaves with a reaction with that velocity, what was the velocity of the deuteron? It's pretty simple momentum problem. We say initial momentum equals final momentum. I'm going to keep my vector notation. My velocities are in the x and y direction. Mass of the neutron, initial velocity of the neutron, plus the mass of the deuteron, initial velocity of the deuteron, is equal to the mass of the tritium times the final velocity of the tritium. All right, because they combine to form a tritium nucleus. I can put in my numbers here. I have a neutron is 1U times 28I plus 17J. This is in megameters per second. Plus the mass of the deuteron, which is 2U, times its velocity, which is 12I plus 20J, which is also in megameters per second. And that's going to equal the mass of the tritium, which is 3U times its final velocity. All right. Notice I'm leaving everything in non-SI units because the units are all going to cancel out. Like you see, this mass unit cancels out all the way across. And so my velocity, when I calculate it using these numbers, is just going to come out in megameters per second. So I'm going to skip a couple algebra steps, but my final velocity... Oh, I'm sorry. I've made a mistake here. I'm sorry. Let me go back and fix this. I don't know the mass of the deuteron. So this is 2u times the initial velocity of the deuteron, and then that's equal to 3u times 12i plus 20j. See, you should always read the question very closely to make sure that you know what's going on. And that's in megameters per second. Okay, what I said before, though, is still true, that I don't need to worry about the units because they all cancel out, and my initial velocity of the deuteron is going to work out in megameters per second. So this is going to be 36 minus 28i plus 20 minus 17j Actually, that should be 36. All right, I have, I'm sorry, not 36. 60. Divided by 2. All right, 36, which is this term times 3, minus 28, which is that term times 1, plus 60, which is this term times 3, minus 17, which is that term. So that is 36 minus 28 is 8i minus, what's that, 43j divided by 2, which is 4i minus 21.5, 22j megameters per second. And so that's the velocity of my tritium nucleus when it goes away. All right, one more question. So it's a little bit different, but it's fairly straightforward. I have cookie sheets on a conveyor belt. This is my conveyor belt. It's going, say, in this direction, and then I have these cookie sheets on them, and I'm dropping cookie dough onto those cookie sheets. And I want to know what force is required in this direction in order to keep that conveyor belt moving at that constant speed. Now I can go to just sort of my basic idea, my basic equation for force and momentum. That force is equal to the change in momentum over the change in time. And all the information that I need is here. Whereas usually it's our velocity that's changing, here it's our mass that's changing. So this is going to be delta m times v, because here my velocity is the same over delta t, and my mass is changing. So the cookie sheets are changing their mass by 12 grams. So it's going to be 0.012 kilograms times my velocity, which is 50 centimeters per second, or 0.5 meters per second, divided by the rate at which they're dropped on, which is 2 seconds. So that means I need 0.003 newtons in order to keep this this cookie sheet moving at this rate. And that 0.003 newtons is, as I've drawn it to the right in this diagram. Right? So it's similar to the football problem where you had to calculate the force, but here instead of the velocity changing, the mass is changing. That doesn't happen real often. Usually we're talking about velocities changing, but occasionally you get the mass changing. I think that's it.